Hi everyone, we're now on the third lesson of our first unit, which is chemistry. Specifically today we're going to look at some main contributions to the current model of an atom that we accept today. Now, as I move along here, there are some very, very early developments that I put here as early beginnings. I'm going to go through these somewhat quickly, and in fact, I might not even touch on them too much. I would like you to be familiar with them. They also are in the textbook. Read through them. These are just the very, very early contributions. Maybe not the most correct, but certainly led us towards what we have today. What I do want to focus on are the four main developments that led to the understanding of the atom that we have today. To begin, we have John Dalton. Now, what John Dalton did is he did a bunch of experiments in regards to combining different elements. So let's be clear. So when you take out your periodic table and you take a look at this table with, those are all different elements, okay? You can see sodium, you can see gold, silver, neon. Now, here's what we know, okay? Dalton imagined that all atoms were like small spheres, but that they could have different properties. They varied in size, mass, or color. Now, what I mean to you is this. If you look at your periodic table, let's say you find sodium. Let's say you could hold one atom of the element sodium in your hand. Let's say in your other hand, you could hold one atom of the element oxygen in your hand. You see, they're both atoms. But here's what you would find, everyone. They have different sizes, they probably have a different mass, and they have different reactivities, different properties. So you see, the thing is, if you look at your periodic table, you find all those different elements. Let's say you could hold one atom of each element in your hand. Yes, that's all, you're holding one atom. But the size, the mass, the reactivity, the properties of each kind of atom are the same. But let me be clear though. Let's say you could hold 10 sodium atoms in your hand. Now those are all sodium atoms. They would all be exactly the same. All 10 of those would be the same size, the same mass, the same reactive properties. So does that make sense? An atom is the same when you're looking at the same element. But when you're looking at atoms of different elements, they will have different properties. Look down here, maybe a more graphical representation. This is one atom of oxygen right here. You can see it has a certain size. It weighs, let's just say it has a mass of 16. You put it on a scale. Right here, this is one atom of hydrogen. You can see it has a different size, a different mass, maybe different color, maybe different reactivity. The point is, atoms are not the same between different elements. And finally, what John Dalton said here is that atoms can combine in different fixed ratios to form new substances. As you can see right here, as we all know, if you take one oxygen and two hydrogens, they will come together and form a new substance, which is H2O or water. Okay, so that's what John Dalton contributed to the model of an atom. Moving along, J.J. Thomson. Specifically here, what J.J. Thomson did, I'll let you look into more the science here, the cathode ray tube experiment. But the point that I want you to know here is J.J. Thomson, what is he famous for? He is famous for he is a scientist who discovered the electron. That is a negatively charged particle. Now that's part of the atom. So you see, if we go back here, John Dalton is all about the atom and the properties of it. But now we're building. J.J. Thomson kind of tells us another piece of the puzzle. What he discovered was the electron. So here's what he has. Some people call it the plum pudding model. It's not exactly correct, but here's his model of the atom. It's a sphere, and what you can see is this green part is a positively charged cloud, and inside of it are negatively charged particles called electrons. So based on his findings, this is what an atom looks like. It's a sphere with kind of this positively charged space, and mixed inside that positively charged space are electrons. Okay, so that's a major discovery. We now have J.J. Thomson telling us about the electron. And just so you know, the electron is going to be used in various courses you might take. Well, this course, Chemistry 20, Chemistry 30, Physics, Biology, it's everywhere. Okay, so we're kind of moving along now. We have some, further development of the model of an atom that we have today. The next experiment here was from Ernest Rutherford. Now, what did he discover? Okay, he discovered the nucleus of the atom. This is a very, very interesting experiment. Okay, now I do have a video linked here in the workspace, and I'm sure we'll do a much better of explaining than I will, because you can physically, you can watch the video and see what happened. But very, very interesting. You see, if we look right over, let's start here on the left. This box right here is going to, think of it as, on a very, very small scale, of course, it is shooting alpha particles in this direction. Now, let me be clear. Alpha particles, they are essentially positive charge particles, okay? So think of it as we're shooting little positive pellets towards this piece of gold, okay? Fine. Now, if you look over here, this is what we have. This, whose model is that? That should be J.J. Thomson's model. So here's kind of the theory. You take these positively charged alpha particles and shoot them in at gold atoms. And, if you look at it, what's happening? The positive alpha particles come right through. Okay? And based on them going past an electron, they might bend a little bit, but no big deal. So here's what they expected. The alpha positive particle should shoot right through and, sort of kind of come out the other side in a straight line. But the results were quite different than what they had expected. Now, this didn't happen, all the time, but here's what actually happened. And the video that I have in the workspace is going to do a much better job than I am. The alpha particles, most of them came right through. They're positive, came right through, came out the other side. No big deal. Here's another one coming right through. Positive particle goes through, comes out the other side. Very, very, if any, change in the course, in its course of direction. But some of them, what happened is, here comes your positive particle. It'd come right in, life is good, and boom, it would get deflected at these weird angles like this, maybe backwards in every direction. Well, what the heck? Why would this positive particle come through and all of a sudden go off in these different directions? Well, what does this mean? It means that we have what now we understand to be a nucleus in the center of an atom. And if you think of it, and if you just let me erase here just a little bit, if you zoom in on this picture now, or take a better look at it, this is our model of the atom, and what we have is a sphere, okay? And within that sphere, we have multiple negative charges. Those will be your electrons. But in the middle of the atom, we have what's called a nucleus. And here's what this experiment discovered. That in the middle of the atom, within that nucleus, we have a buildup of positive charge. And that's why you see, remember, as you know, like charges repel each other. So what happened is that positive alpha particles coming through, and it hits something that was also positive. Positive charges want to repel each other. So it's kind of like it flew in, hit the same charge and took off, tried to avoid it. This is a big discovery. You can see the difference. If you take J.J. Thomson's model, it's kind of this, overall positive charge with just negatives mixed all over the place, the plum pudding model. What we actually now discovered is we have a much different model. We have a sphere with kind of this, electrons scattered throughout. And in the middle, we have what we call a nucleus. And we now know that the middle of the atom has a nucleus, and that nucleus has a positive charge. And that is the result of the Ernest Rutherford gold foil experiment. Please watch the video, which again will do a much better job of explaining than I will. Moving along, this is also interesting. This is very important for reactivity. We have Niels Bohr. And what Niels Bohr discovered was that the electrons don't just float everywhere around in an atom, there actually are different levels, okay? Now what I mean is this: if you go back to the plum pudding model, and I'm focusing right here. See this, everyone? Or maybe, sorry, that's actually wrong. Let me go to this one on the right-hand side. If you look, we have the nucleus in the middle, and the electrons are just kind of, varied all the way around. So here's your sphere, and within the sphere, in the middle, you're going to have a nucleus, and the electrons are just everywhere. That's not what actually happens. The true model is this. If you look over to this point, in the middle, you have your nucleus, and the nucleus is going to have a positive charge. But what Bohr discovered is that the electrons essentially exist around the nucleus in different levels, and each level can hold a different number of electrons. So for example, the first level around the nucleus can hold 2 electrons, or 2 negative charges. The next level, the third level, can hold 8 electrons or 8 negative charges. The final level, or the third level that we are responsible for here, I shouldn't say final, can also hold 8 electrons. So if you look at this here, so the first one held 2, the second one held 2, and the third one, well, what it should say is, for our purposes, it'll be 8 electrons. And this is going to lead to what we know as the 288 rule. So what's different here now, everyone? Niels Bohr, what he adds to it is, we have a nucleus, and we know the nucleus has a positive charge. We know that the electrons occur in levels around the nucleus. The first level can hold 2 electrons, and I'm just showing you here. The second level can hold 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8. And the next level can also hold 8 electrons. And that's going to be very important for reactivity. So do you see the difference here, everyone? If we go back a step, this model of the atom has the nucleus in the middle, and it's positive. That's not changed. We know the electrons kind of float around, but in this model, they're kind of just floating around everywhere. Whereas now, based on Niels Bohr, we now know that the electrons, they are still outside the nucleus, but in a very specific arrangement. Almost in shells, in levels. The first level can hold 2 electrons. The second level can hold 8 electrons. And the third level can hold 8 electrons, despite what we have here. So moving along, so what do we have today? Let's just make sure we have this, okay? Now, this is the quantum mechanical model of the atom. I don't necessarily need you to be familiar with all this shape. The point that I'm trying to make to you is, we take this all together now, and as science has advanced, we have kind of an accepted model that I would like you to work with moving forward. And it is like this. So remember, in the middle, you have a nucleus. Okay, so here's the nucleus. Whoops. Now, inside the nucleus, here's what we have. Okay, all coming together. Inside the nucleus, you will have positive charged protons. So inside of there, you have positive charged protons. Also found inside the nucleus will be, I'll put N. And those are going to be called N for neutrons. So inside the nucleus, we have 2 different kinds of particles. We have positive protons, and we have N neutrons. They are neutral, as in they have no charge. They are not positive, they are not negative, they simply have no charge. Then floating around the nucleus, we have 3 different levels. First level, second level, and third level. And if you remember, each of those levels can hold a different number of electrons. I'll go to red here. So the first level can hold 2 electrons. The second level can hold 8 electrons. Let's fill this in here. And the third level can hold 8 electrons as well. 1, 2, 3, 4, 6, 7, 8. So again, in recap, you have your nucleus. Within the nucleus, you have positively charged protons. You have neutrons. We didn't really talk about them too much, but they're in there. It's another particle. They're called neutrons. They have no charge. They are neutral. Surrounding the nucleus, we have 3 energy levels that we at least are responsible to know in high school. The first level holds 2 electrons. The second level holds 8 electrons, and the third level also holds 8 electrons. It is key to understand this because moving forward, this is how we're going to understand why certain elements react with each other.